Okay, everybody, we're back again for another edition of 5114. I want to give a very basic statistics lesson before we even start up with a conversation about decision theory. Everything we see in the world has to do with decisions. And we hear a lot about the models. The models are saying this. And we had a conversation a couple weeks ago about right now a lot of the models in the world, whether it's financial models, the epidemiological models, whatnot, they all might be changing right now. And so we don't have good control over the variance of everything. We don't know what we're modeling. We don't know how much uncertainty there is. And that was true weeks ago. It's always kind of true a little bit. Models are always changing, but maybe we can understand, what we're modeling and update our models periodically. Here's a really big problem right now, and this is just a Stat 101 thing. The data we're collecting is not very informative. And so we have very lopsided data. Who are the sickest people? What do they have? We have this conversation about surveillance data, going out there into the population. Should we just test everybody? And it's kind of a funny conversation that you hear on the news one way or the other. People saying that's phase 2 stuff. We can't go in and test everybody. We're going to do that in July. I want to remind people about statistics. You don't actually need to test everybody. You can randomize. You can design. You can go in and get just a little bit of the people, small percentage, and have mathematical certainty about maybe average effects, what we know on average. Individuals might require more sampling. But without the right data, it doesn't matter what the model is. You can have perfect models that can adjust to everything. They have enough parameters for all the flexibility and the differing trends that we see. But if we do not have the right inputs, i.e. the right stuff that we estimate from data, it doesn't matter what those models are. And as a statistician, what I usually tell people, if they don't think they even have the right data or they bias the sample, is the model doesn't tell you anything. Like, it can be completely misleading. It's hard to, you can't really recover from that. Unless you know where the biases are. And eventually, we're going to start estimating that. So what I'm kind of alluding to is, out in the population, we need to know if we're going to estimate a rate, not just how many people have a disease, but also what population has been exposed to COVID in the first place. So we need to be able to estimate both the numerator and the denominator. So the number of people that have been exposed is a very important thing. And so any Stat 101 person would be able to tell you this. But as a statistician, I can never really get past, if the data is not informative, it doesn't matter what I do with my models. No math is going to save you. So a lot of times a statistician is just there to tell you some basic stuff. Sampling theory, going out there and just kind of estimating what's going on in the population. If you see something that's interesting, then maybe you do more refined sampling. So you can do adaptive sampling as well. Okay, more decision theory. In a nutshell, it says you can't make decisions unless you have the right sort of data. Model's part of it, but we also need the right data. My class is a bit of a fiction because I'm always saying I know where the data came from. So I get to know F, and that's a big deal. I'm also saying I got that data from that model. So I don't just get to know F, I'm also saying I have unreliable data points. The real world is a lot harder than that. And that's what we're noticing right now, and people are arguing over which data they should even get. I suggest a statistician to help you with this. Okay, back to decision theory. We've made a whole bunch of claims about stuff. I've got a couple links online, so back to our web page. I have a couple statements here from the ASA. We're going to get to those in a moment. So in hypothesis testing, I think the next couple lectures are going to roll into Chapter 8, and we're going to start touching on hypothesis testing. I want to just point you in a direction of a couple statements you might want to read before we get into all of this. This is a contentious topic, and a lot of times people are arguing over optimal techniques, but they're arguing over the optimality criteria in the first place. And they don't really realize it. We'll get into that as well. So some of this stuff that we confront in decision theory shows up in Chapter 8 in hypothesis testing. I have a paper online for you. So this is the empirical Bayes and Stein estimation paper by George Casella. It's one of the authors of your textbook. This appeared in the American Statistician, and there's an empirical Bayesian estimation technique that they go on to show destroys the MLE in a very obvious sort of problem. And it's surprising to people. It's called the Stein Paradox, but it's not a paradox, it's just math. And it's kind of an obvious result in some ways. I say that fully acknowledging that when I first heard this, I was baffled by it, blown away just like everybody else. This example will show you that this sort of optimality in, what's the right estimator is a little bit of a contentious question because you can define that in lots of different ways. I'll explain what I mean by that. There are some things that I do, and I can kind of govern where I operate well in a parameter space. And there's some code online. This is some MATLAB code right here that implements the examples in that paper. So I'm going to write down some facts from this paper, and I'm going to leave it as a homework assignment for you to try to read through that paper. I think it's a good exercise. We'll be looking at it just a little bit later in this lecture. Okay. We'll be doing a little bit of simulation later. Let's just go back to decision theory. So, we've discussed two different criteria. So, we've discussed a lot of criteria, I should point out. But the ones that we kind of focused on last time were the minimax, criteria for finding an estimator, and Bayes estimation. The difference here between these two things is a maximization and an averaging. So the Bayesians are averaging, and the minimax are doing an optimization in that space. So let me just write this down. So the minimax estimator, estimators are functions of the data. And I'll write down MM for minimax. This is equal to the minimizer of the maximizer of the risk function. So this is risk. So that's the integrated loss function, where you're integrating over the data space. And so this is a function of E, the estimator itself. You actually take this out. This has been integrated out of this space. So the data is integrated. So this is just my function right here. So I think I misspoke for a second. But this is a function of an estimator and the parameter space. And so I'm going to look over the maximum of the parameter space, and I'm going to find the estimator that minimizes that risk. So the Bayes estimator is similar, but a little bit different. I'll put down EB. I also want to remind you, there's a prior that's used in this. And this prior function is the weighting function. It's how much weight you're putting in different parts of theta. And so I want to remind you that's always in here. Even though the parameters and data have been integrated out, this functional form matters. So this is the prior. And I'll just write down that that's just a weighting of theta. Weights on theta. So you could have information about what that parameter space is and how much you want to put weight on different parts of the space. So this might come from some economics, some utilities, something outside of the problem. Who knows? Lots of stuff you can do there. Very context specific. This thing is also a minimum over the same parameter as before. E, the estimator itself. But instead of maximizing R, I'm going to integrate it. So integrate R so I'm going to look for the estimator in here where the average risk is lowest. And this is how I'm averaging it. So this is a weighted average. Bayesians are weighted averagers, if you haven't noticed that yet. So that's what they do. It doesn't sound so contentious like that. There are a lot of optimal averaging processes, so you can get things right on average in certain ways. But always ask, what does the average mean? We're going to leave it as a general problem right here. But these are kind of similar to each other. So I want to tell you a few things about these estimators. We've alluded to this last time. So one thing that I'll mention is if pi theta is integrable E pi b, the Bayes estimator, the solution to this problem, is admissible. So let me tell you what this word means. This says, compared to every other estimator in the world, no matter how you came up with it, whatever it is, some function out there that tries to estimate theta, E pi b, so I'll say this thing right here, estimates theta best somewhere. Okay, what I mean that is, I mean that in the average sense. So let me just write that down. On average, where the average is over x. That might seem confusing to you. Let me just draw a picture. So on my y-axis I have risk, and this is a function of a parameter space right here. So imagine you had some estimator and its risk curve looked like this. I'm going to remove a point. And I have some other estimator. So I'll write this down as E1, and this is the risk function for E2 over theta. So this is estimator 2's risk function, this is estimator 1's risk function. Okay, imagine these were the only two estimators in the whole entire world. So you'll have to use your imagination because in real problems, I can come up with infinite collections of things. This one looks like it's always lower, right here. Turns out, this one right here, I'm going to put its risk function right up there. And I'm going to make this one a little bit lower, over there. So estimator 1 is lowest right here. It's also smaller than this other one right here at this point. So it's smaller in 2 places. And so that means it's better somewhere. It's better in these 2 places, right here. Estimator 2 seems to be, or estimator, yes, 2 seems to be lower almost everywhere except for those 2 places. And so an admissible estimator is said to be lowest somewhere compared to everything else. And these are pairwise comparisons that you're making. So I compare to something else, and I just see if I'm better somewhere. And if you can do that to everything out there, you're just better somewhere, doesn't all need to be in the same place, then you're admissible. Okay? Usually, the typical sort of definition to all of this, we'll talk about a dominated estimator. So let me just write that down real quickly. What a dominated estimator is. So these are unadmissible estimators. So I'll go the other direction, if you will. So an estimator is said to be dominated if another estimator exists such that it's better everywhere. Clear a little bit of this up. What I mean by better is that it's on average better, i.e. the risk function is lower. So this is on average over x. So i.e. the risk function is lower. Everywhere. So this is a statement about theta. So this is on theta space right here. So let me show you an example. This is easier to show because I don't have to hypothesize about these only being the 2 estimators in the world. What I'm kind of imagining, if these weren't the only 2 estimators, I could maybe exclude other ones that lived up here that were uniformly worse. And so that's something you have to use your imagination to think about. Let's imagine I found an estimator. So let's say you came up with an estimator. So I'll say this estimator, dominated estimator, I'll say this is E dominated. Been beaten. So I'll say maybe I've got some risk function. I'm always drawing straight lines if I can, but these things can move around. I'll say it ends here. So this is a function of theta. This is risk. This is the risk function over theta for E dominated. Let me just call it E dom. This is dominated if there exists another estimator out there that is lower everywhere. So here's some other estimator, I'll call it E star. It's a function of theta, and it's lower everywhere. What that is suggesting that on average is a function of x, might not be true for one particular data set, but over the whole averaging of all data sets, this has lower risk. It is conceivable that for some particular data instance, that this estimator does better than that one. But this is saying, if this is a risk function, this is on average lower. So this will dominate this. It's always lower. This is always worse. So we say it's dominated. So another way to put this together, the admissibility and domination, is to say that admissible estimators are not dominated by anything. So let me just put this together. To find that an estimator is inadmissible means that you can find another estimator that beats it everywhere. I'll throw in the one caveat. If this estimator, for instance, if I lost a point right here, and I put this right on top, right here, this is still dominated, even though it ties it right there. And so it's got to be better at some point to not be dominated. So I'll say this is a tie, so still dominated. So the definition of an estimator that's dominated is a risk function that's higher across all theta, but you can have equality at some points. That seems like a good thing. You probably don't want to use dominated estimators. But it's harder than all this. And so I think that's where my last example is going to really help you out to think about it. But what we just learned is this definition of admissibility, and we have this theorem. If this is integrable, so what I mean is that I can take my prior, and if it's normalized, it's equal to 1. If it's not normalized, this will be some finite number. And so it's normalizable. I can actually do that integration. Remember what we've said about Bayes so far is that if our posteriors are integrable, well then you can maybe use it for something. If it's not, it doesn't help you to do anything. And so this is a stricter condition. So some people call these proper priors. So that's just some lingo. So if you're familiar with the Bayes paradigm, you probably know that term. So for proper priors, your estimator is admissible. The problem is, in this, it does not say that if you use an improper prior, you're not admissible. So the converse is not true right here. X bar can be an example of that, using a flat prior for estimating something. You still get admissibility, but this theorem doesn't kick in and give it to you. If you are using a proper prior, your Bayes estimator is better somewhere on average. That's cool. We can't always say that about MLEs or any of the other techniques that we've done. And so MLEs won't necessarily have this criterion right here, that they're always admissible. And we'll look at an example in a moment. But what this does say is if you are doing Bayesian inference using a proper prior, you're better somewhere, and that's guaranteed. I want to say, I think this is what a lot of people are doing out there in their research universe, is they engineer a prior, and it'll work better on some problems than other problems. And then they go and they find problems where their prior works better. A problem that you oftentimes see, and I study this in my Bayesian class a little bit, is the model selection prior. So how do you place zeros on things in a linear regression? And you see a lot of research going on that they're like, I'm better over here, I cross-validate it better than this other technique. I think really what's happening is they're just kind of exploiting this, that you're better somewhere in the problem. So different levels of sparsity in the problem, a different estimator is going to operate better. So this is an infinite game. You can do this forever. So I think it's just better to try to understand what's really going on and how do you engineer something, how do you pick a prior so that you're better in the places that you want to be. And so that kind of brings us about to subjective priors. I'll show an example in a moment, but we'll prove this in a second. I want to show you one other thing. We said this on Friday. That if the risk function for my Bayesian prior is constant. Okay, so there's a whole bunch going on. I didn't just plug any function in there. I plugged one in that I found solving this equation. So I wanted to minimize over the average risk, where I've got some sort of a prior distribution, d theta. I'm going to minimize this over e, and that's the thing I plugged in here. So if this thing is constant function in theta, so what that means is that my risk function is flat, straight. Then EB pi is minimax. And I kind of describe this as the least favorable thing a Bayesian can do. Doesn't mean it's not something you don't want to do, it's just that it's kind of the worst one of these minimax estimators because it's constant everywhere. Maybe that's good, maybe it's bad. If you can bring it down in other places, you would like to do that. And that's why this is called least favorable sometimes. But this is kind of a fun thing to think about. And this is really, both of these claims are kind of nice. I at least know how to engineer a minimax thing, is I pick the prior such that this thing is constant. So you might say, hey, that's not fair game because you're going to start averaging over different thetas. So what usually people do is they'll go to their prior and they'll take the knobs in their prior, i.e. the tunable parameters, the hyperparameters, and they'll turn those so that this thing is constant. You'll get a freebie minimax estimator out of it. It's also admissible. You're going to beat somebody somewhere with it. Let's prove these. Sometimes when I do this, people are kind of baffled and they're thinking about it, and there'll be somebody sitting right next to them going, of course. So the proofs actually are fairly intuitive. If you understand how an average works, you've already done this in your mind. But there might be a few little steps in here. So let's just think about it. This has got to be true. So keep in mind, I'm not doing anything funny with my weights. They sum to a constant number. So real weighted average. So there's nothing like pulling things off to infinity in some parts of the space. So this prior isn't blown up anywhere. So it's a regular average, not anything weird up my sleeve. So that's the problem with the improperness, is I can do a lot of things when I let things go off to infinity. A lot of math games you can play there. Sometimes that can yield good stuff and sometimes it can be problematic. So we'll just keep our case to the proper prior. Proof. If it's proper prior, then I'm admissible. So admissible means is best on average. This is an average over both x, the data space, and theta. So the averaging over the theta space is what distinguishes you as a Bayesian. It's best on average. So I'll just say what is best on average right here, the risk function. So my risk function is best on average. Admissible says you're lower somewhere. So just see if I can conclude right there. So lower somewhere. I'm going to leave it there. This proof is pretty obvious. What it says is that you're lower on average, so you're lower somewhere. It's got to be true. You guys watch NPR, Garrison Keillor, Prairie Home Companion. There's always this little thing where it's like children at Lake Wobegon were all better than average. So all the kids are smarter than average. Can't be true. Somebody's got to be lower. The average is in the middle somewhere. And so if you're lower on average, you're lower somewhere. That's the proof. If you want to set up a contradiction proof, you can do that. So if you want to be mathematical about this and write down, okay, I'm going to assume that it's not true, but I'm lower on average, you'll reach a contradiction real quickly. So it's not possible. Let me write it out. So let's say, assume risk of my Bayes estimator is inadmissible. So I'm going to assume this is true. I'm going to compare it to some other estimator out there. And I'm going to say that this estimator right here is always lower. This one Bayes estimator. This is some other. So what I've set up is that it's inadmissible. That's my assumption. That's what that says. Now, if you want to build in every once in a while, you can have a tie in here. You can add that extra line. If I were submitting this to a journal or something, I'd add the extra line about that it could be equal in some places, but that there was at least a place in here where the inequality was absolute. So I'm going to take both sides. I'm going to hit it with the same prior. So remember, you've chosen your prior when you're doing all of this. So I do all of that right here, and I integrate both sides. So d theta, d theta. And since that's true, and there's nothing funny going on, these are all just positive weights, that's still true right here. And so when I go to minimize this, that yields that estimator back. And this, once I minimize this, is supposed to be lower on average. So I have a contradiction, however you want to write this. Since E pi, Bayes, is a Bayes estimator. So this is min over E here. That's my proof. I like the idea. You're lower on average, so you're lower somewhere. But this is what a formal proof might look like. And so I have to remind you what this thing was. It was derived because it was lowest on average, which contradicts this equation that we just got, where we assumed it was inadmissible. So the logic in the proof says contradiction, and so this can't be true right here. So it has to be lower somewhere if it's lower on average. Leave it to the mathematicians. So 2 is a little bit harder to prove. I think that 1 is true just kind of by definition of averaging. So this takes a little bit more thought. So this is the proof for 2. The minimaximality of things. So if I come up with a Bayes estimator and it has constant risk, it's minimax. And I can just say that. Let's just remember what the minimizer over here on E, what am I looking at? I'm looking at this function. And there's a pi in here. And I can do some nice bounding by the maximizer of everything. So just remember what this thing is right here. This is an averaging over the loss function. Now, if this thing is constant, then I'm going to be able to pull this thing outside of the integration, right here. So it's going to have nothing to do with this, if it's constant. I want you to think about this, right here, R E hat minimax. So this thing right here, the minimax estimator, something like it, it's always going to be bigger than what's going on average. So I'm going to be able to bound all of this. I'm going to be able to set up this bound because this is a maximizer of everything. But this is constant and it's lowest on average. So I want you to think about this for a little bit. What has to be true about this? It's lower on average, it's admissible, it's better somewhere, and it's constant, and it's bounded by this. See, our wheels are turning. Starting to see this. It's lowest on average, it's also constant, and this is just true right here. So if I plug in the minimizer over the maximum of the space, this is bigger than that over there. Lowest on average and constant. It must be running through the minimax point. Let me think about that. It's a nice brain exercise. You'll reach a contradiction real quickly if it doesn't do this. So remember, we have to use the fact that this is minimizing everything on average and it's constant. This integration is not acting on this right here because it's constant. This bound always holds. So how did I find this thing right here? I plugged in the estimate that minimized the maximum on this. I probably need to write in here maximum on theta. So I've averaged this. So apologies, this is important. That's the thing that's making it bigger. It's biggest somewhere. So that's what I plot down. So try to draw a picture. That's what I usually do for people and say, let's think about what would happen if this is not true. So work on that and maybe we can go through the formal details here. But this is extremely important. It means that a Bayesian has an operating tool. An averager has an operating tool. So what does the Bayesian do? They look at the posterior distribution. So note, the Bayesian forms the posterior. This is proportional to the likelihood times your prior. Same prior that we've been talking about with decision theory. If you're going to turn this posterior into a decision, then you minimize the posterior expected loss. So E pi is equal to this. The minimizer over E So the Bayesian's problem, this is equivalent, we proved that last time, that double integral breaks down to this right here. So this is the expected posterior loss. For example, if your loss function is squared error, the minimizer right here, it's easy to find. You can do it by direct calculus. You'll find out that it's the posterior mean. If your loss function is L1, you're going to go after the median of that distribution. This estimator is going to have some reasonable properties. It's going to be admissible if I use a proper prior. Oftentimes, if you have an improper prior, it'll also be admissible. We don't just get that for free, though, from our theorem. I could, if I wanted to turn the risk function constant, I could say something about minimaximality. I want to show you something surprising, though. And so we've been asking these questions, like what's a good way to form estimators? Well, it depends, again, on what your utilities are. We have some techniques for doing that. We've got MLEs, we've got Bayes in the first place. This kind of goes hand in hand with all of that. We have MOM estimators, they might have nice properties as well. And what we really need in practice is operating tools, not just theory, not just theorems, and not just answers like, well, it depends. I want to show you something pretty cool that you can do as a Bayesian. It will surprise you. Let me show you a problem. This is the Stein Paradox. And what I really want you to take home from this is that a lot of this theory is complex. And it's surprising what can happen. Just because you have an estimation technique doesn't mean that you're just always going to be best. You might be best in some sense. The Bayesian is at least giving us a method to be best on average. Where are we good? Probably in areas where we put a lot of mass in our prior. That's where we're going to start to look pretty good because we've anchored everything in there. So if our prior is establishing a lot of mass somewhere, we're biasing the problem. And so that has a benefit of reducing variances in that area. And over in that area, you're probably going to do pretty good. Let me just think about this problem, the Stein Paradox. Okay, so I'm going to tell you a little bit about this, but I'm going to give you an estimator. Some people call this the James Stein estimator. I'll throw a pi on there. So the way we might derive this is a Bayesian. There are other derivations to this estimator. I put a paper online that you can look at, and it will walk you through the full derivation of this. But I want to set you up a couple different estimators, and I want to compare to the MLE, something that is going to be a little bit surprising. But let me tell you what the problem is first. So xi's are going to come from this distribution. This is all IID stuff. I think that's important to state here. Because the estimator we're going to come up with, this one is going to dominate this one right here. And I think a little bit of intuition can be gleaned from this example. I'm going to say I goes from 1 to P. Okay, so this is the dimension of my problem. Now this problem's a little bit funny, in that for every theta I get my own xi. So each xi has its own mean. This doesn't make any difference that this is constant sigma right here. This is not the part that makes a difference. It'll just make everything easier. I want to point out this example is equivalent to this other example. So this example is equivalent to an example where I had multiple repeats from this right here. So if I let this be n theta I sigma squared, I goes from 1 to p, but I gave you repetitions in here. And this doesn't even have to be the same number either. All the mathematical consequences will be the same in all of these problems. This one sometimes confuses a little bit of a few people, but let's just think about this. What's the MLE for this problem? Usually I would have you think about this for a moment, and somebody would figure out pretty quickly theta hat MLE, and this is going to be for all of the different i's. Remember, there's I of these. We're going to need to estimate them. I'm going to say this is known. If we didn't know it, we could estimate it, and all of the consequences will stay the same. Okay, so a lot of these are just simplifying things in the problem. They don't actually make any difference. So I'll say that's known, doesn't make a difference in this problem. I'll say we only get one data point. I'll remind you that if I know this, the MLE for estimating theta I, in this problem it's really easy to see, I'll write down I right here. This is going to be X bar. Well, I'll write down this. Sum X I j over n. So I'll say this is X bar I. That's the MLA in that problem. If I didn't know this right here, I'd need to see at least 2 data points to say anything about theta. So hopefully that's clear. But the MLE for this problem has exactly the same answer. I'm going to average together one number. It's just going to be xi. Okay. There's nothing weird about this. Problem we'll solve here and write down a solution to. Everything extends to this problem. So you don't need to be worrying. Is this going to happen? This paradoxical thing going to happen because I only used one data point? No. Is this paradoxical thing going to happen because I assume that I've known sigma? No. So this paradox still happens. Okay. So let's just stick with this problem. It's a little bit simpler. Remember, I goes from 1 to p here. If you had repeats, you'd estimate it like this. If n was different for every I, you could still do the exact same thing. Okay, so nothing weird in all of this. Turns out, when the dimensionality of this problem is 3 or greater, this estimator is inadmissible. And that's going to surprise you. So here's a fact. This estimator if p is greater or equal to 3, theta hat I, the MLE, is inadmissible. Now, the punchline to this is not going to be, don't use this estimator. That's not what I'm going to say. I'm going to say it depends. I'll try to be almost humorous about it in a case where it's kind of obvious, where you would know whether or not you wanted this, or if you even cared about anything here. Keep in mind, all of these are IID, right here. One of the punchlines is going to be, if I entangle all of these xi's, I can do better. And that's going to surprise you, because you're going to say, no way, because they're all IID. They don't have anything to do with each other. So, and I've already discounted the fact that these having the same sigma doesn't change any of that. If you want to index sigma, you can as well. You just need 2 data points if you didn't know the sigma. Okay. There are a lot of different James Stein estimators. I'm going to write one down. And then I'll tell you where they derive it from, and you can look at the paper for any details there. I don't have it memorized. Just 1 second, you guys. It's messy. There are different versions to this estimator. This is a particular James Stein estimator. Here's one. This probably isn't your best one. So P minus 3. P is the dimensionality. I will make a note. This is for P greater than 4, greater or equal. So this result is true. Right here. This estimator almost shows this. So we're going to be off by one thing right here. We're going to be taking P minus 3 and we're going to want that to be positive. There's other ways to do the derivation, and I'll link to that in a moment when we look at Casella's paper that I'm pulling this directly from. So this is just kind of a fun thing to talk about, and I think that there's some pitfalls to the way they've done it, but it's also illuminating in terms of thinking about why everything works. And maybe that's what they intended. I'll assume that's true. I'll walk you through the derivation of this in a moment, but I don't want you to worry too much about it. What we can show is that this estimator right here, so this is the sum of two pieces, is better than this everywhere across all of theta. And that's going to shock you. Let me just write that this was derived using an empirical Bayesian technique. I'll tell you what that means in just a moment, but it's a Bayesian technique where I'm allowed, with restrictions, to take my prior and throw some data into it. Okay? If you're an ardent likelihood principalist, you call foul. I used to think that this should never be done, ever. And I've changed my mind on that there are cases where I'll do it. It leads to a very interesting result in this problem. But this uses data in the prior. In the prior that they use, pi on theta I, so on each one of these thetas, they're going to place a prior. And the prior is going to look like this. Normal, mu, and tau. Now I want to point out something. This is actually the important bit of all of this. This is where the Stein Paradox, which is not a paradox, but the Stein effect happens. It happens because this is common to every theta I. So I want you to think about this just for a moment. I'm just going to draw you a little picture of everything. Each theta I, so theta 1, theta 2, theta 3, down to theta p. These all have an associated xi. x2 there, x3, and x4. So this is just a graphic depiction of this. If I were in this case right here, I'd have the x bars would be the sufficient statistics. Picture would look the same. But all of these theta i's now have some gravity towards this thing mu right here. So what the Bayesian is doing with this is they're pulling everything towards mu. This is actually the Stein phenomena, so where it all comes from. So I'm going to say this is shrinking towards mu. It's pulling everything towards mu. This is regularizing the space. This is a good thing to do. It does have its repercussions, though. We're biasing all the estimates. So notice that these didn't have any relationship to themselves in the original problem. And I have these xi's that are coming out that I used to estimate these thetas, presumably. But now I'm entangling everything, I'm shrinking everything. What this does is it puts a little bit of pressure on the space, and it controls your errors. So it means that the errors I go and I try to, the errors I make in estimating each one of the theta i's by doing this, here's the mathematical thing, here's the pictorial thing, by pulling everything, I start compressing all the errors. I start treating them in kind of an average sort of way. And it should be no surprise to you that you can do a little bit better when you do that. There's also a lot of bias in everything. I'm biasing everything towards this. But my trade-off is going to be to shrink the variance and everything. I want you to think about what this estimator is. So I'm going to call this E. James Stein. Okay? This is a function of all of my data. These two things. It kind of looks like this estimator right here. That appears right here. But it's some sort of a weighted average. So notice that these two things right here, they sum to 1. And so I'm taking an average between the MLE and x bar. So x bar is just the xi's divided by p. Okay, that's all that is, the typical thing. And so I'm shrinking everything towards the average, and that regularizes the errors that I can make. And it biases them towards whatever I was kind of thinking in the first place. Turns out, instead of just plugging in these values right here, they ended up picking some values to plug in right here. So the empirical Bayesian technique is going to pick data values for this. And so an empirical Bayesian acts like a Bayesian, except they plug data into these. Okay. There can be some major repercussions if you do that wrong. But let me show you what they did to get those values. But ultimately, the whole Stein thing happens because this is common to all theta. And it sets up a mechanism where everything's being kind of co-estimated together. And because of that, it regularizes the error. People didn't like this very much. So back in the 60s, people were freaking out over this. This is not good. All of those data points were IID. I shouldn't be able to use other data points to estimate theta I. So I'll just be clear about this. This thing right here is theta I hat. So to estimate every one of the theta i's, I'm using all the xi's. But the original problem was all IID. So the original problem looked like this. normal theta I sigma squared. Okay. Let me show you the paper. Derivation all happens in the first page or two. I know that a lot of you cannot read this. There is on live right now, but if you go to the web page, you'll be able to pull this paper up. Okay, here's the original problem. xi's are normally distributed with mean theta I sigma squared. That's what that says. So the original problem setup. My prior is right here in line 2.2. So same exact prior. Normal with mean mu, common to every I. This is what's happening. This is the shrinkage. That's actually the mathematical magic wand that makes all this happen, is all of these things are getting tugged into there. The typical Bayes estimator, now they didn't say this right here in this line, but they've assumed a loss function in all of this. And the loss function that they've assumed is L2. And so that induces the Bayes estimator is the posterior mean, and that's it. And I've asked you to work through a homework problem or two that has you walk through this calculation. This is the posterior mean. The posterior mean is a superposition between the data mean. If I had more repetitions right here, this would be x bar, but this is x bar where I just have one data point for each theta I, and the prior mean. How much weight am I putting on it? It depends on how diffused I make my prior. Okay. So that's my Bayes estimator. Now things get empirical. We've never discussed what these two parameters are. Here's what an empirical Bayesian does, is that you become not a Bayesian for a second. They want to try to estimate the hyperparameters in everything, and what these two parameters are. Now you might say, well, you could be a Bayesian and you could put a prior on them. I mean, you need to put a prior on something else and keep doing this forever. So you can't really do that in a meaningful way. So line 2.6, they do a moment matching approach. So this is what they do, is they marginalize out the parameter space. So they come up with the distribution of f of x. So f of x is simply the marginal distribution of x where I've integrated out the thetas. And in Kinsella and Berger, they have you walk through this problem. They have multiple repeats on everything, so they have a divider by n there in the Kinsella and Berger problem. But this is the margin. You can figure this out by iterated expectations if you wanted to. That would give you that. And the iterated variance formula will give you this. That's the easiest way through it. I always recommend everybody complete the square once in their life and do it the long-winded way. But this is the solution to an integral where I've integrated out thetas. So that's the marginal distribution. So where is it centered? Well, if you didn't know anything, it's going to be centered where your prior was centered. How much variance is there? There's the variance attributed to your prior and the variance attributed to the data point, and those add together. That's conceptually easy to swallow, but you'd probably want to derive that. Iterated expectation and variance will do that for you. So here's what they do. They take this distribution right here, the marginal distribution, so they find the expectation of it, and they find the variance of it, and they figure out some empirical forms of this. So what they end up doing is they look at the expectation of x bar. Everything is IID in all of this. So expectation of x bar for these p data points is mu. And this is what they do with that information. They take mu and they set it equal to x bar. And they put a hat over the mu. That's method of moments. So they match the moments right here. They know this is a mathematical exercise, and I would say this is probably why this isn't the best James Stein estimator out there, is they moment match on this function of the data. They know what it is, so this is a moment match, expectation of that thing, and I know what it is analytically. I'll point out to you, this is an inverse chi-squared distribution right here. So if you went to Wiki, you could probably verify this to yourself. So the expectation of x bar is mu, and the expectation of this function is sigma squared over sigma squared plus tau squared. And they set these both equal to each other, and then they estimate them. Let me write down that last step for you. But at the end of the day, they'll come up with estimates for mu and tau squared, and they'll plug them all back into everything, and they'll get this form right here. So they'll go back to the Bayes estimator. This, and whatever they solve for mu, they plug in right there. So if we just look down here, what they did with mu, they took mu, set it equal to x bar, so that's my mu hat. They went back up to this formula, they took the mu and they replaced it with mu hat, and that's x bar right there. They do the same thing with tau, they replace it. So they solve this thing where they match that to this function. They solve for tau. When they replace everything, they write this down. And the rest of the paper is all very interesting. I'll walk you through a simulation exercise in one moment. Let's move back over and I'll do that last step on the board. But you'll want to look at the paper, the companion. I am not going to test you on empirical Bayes. In this class, I'm just showing you this is one way to do everything. This will still happen. The result will still happen if I just plugged in any numbers for mu and tau. It just might solve a problem that I'm not interested in solving. It might be good for some values of mu. But this is what they've done. Took expectation of x bar, they set it equal to mu hat, or they set it equal to mu. That is mu, sorry. That is true. And then they wrote this down. P minus 3 sigma squared, sum of the xi's minus x bar squared. This is a ratio of those two things. You can solve this. They don't solve this for you in the paper, but this is something that you can solve. This is inverse chi-squared. Everything's normal, so squares. The normals are some sort of chi-squared. This is being normalized. So here's what they do. This is the empirical Bayesian step. This is one empirical Bayesian step. There's many ways you can do this. I'm going to call it the MOM method. So MOM empirical Bayes. Which MOM estimator? Well, it depends on which one you did, and you can come up with different answers on all of this. You can see where the P minus 3 has come from in all of this. It makes it so that's equal to that. P's got to be bigger than 3 to do this. This can't be a negative thing, and you can't call that a chi-squared. So this says mu hat, and I'm going to call it empirical Bayes, is going to be x bar. That was really a MOM estimation step to do this. So I've just blended techniques. Tau hat squared, I'm going to get by taking sigma squared over sigma squared plus tau hat squared, and instead of writing down the expectation operator, I'm just going to remove it. I'm going to get p minus 3 sigma squared over sum of the xi's minus x bar squared. I'm going to solve for this. Then I'm going to plug all of that stuff back into line 2.3 of the paper. And it's going to produce this estimator. So this estimator, let's remember, it didn't matter what my hyperparameters were. I used a proper prior. So it means that this estimator is admissible. It's lower somewhere than something else. As I compare it to anything else, it's lower somewhere. And I will tell you, this is not necessarily minimaxed by our theorem, because it's not constant in terms of its risk. But it turns out, what we're going to find out is this is bounded by something that's minimax, and so it turns out it is. And that turns out to be fascinating. This is, again, supposed to surprise you. How the heck am I going to beat the NLE? You know, something like that. I'm going to use data that is not informative about theta I, and somehow I'm going to better inform theta I. I want to show you the simulation of all of this. So I did something a little bit different in everything that I've done. And the paper also does this. I did this for illustrative reasons, but I changed this a little bit. So for my simulation, I'll write this down. For my simulation, I used mu hat is equal to 0. This is where the mu came in. This is where we plugged in the mu hat into that formula. And instead we plugged in x bar in all of that. What I'm really saying a priori is that thing's 0. So I'm going to shrink everything towards 0. And then I'm going to do exactly the same thing. I'm going to come up with a mom estimator in the same way, but I'm not going to treat mu. I'm just going to say that's 0. And I think that's important to do so that you can see where everything is being shrunk to. So you know what it actually is. And so where we're actually getting all of the influence. So Bayesian is putting bias somewhere into the problem. I'm biasing my answers towards 0. How much bias? Well, it depends on what my tau is going to be. My method of moments estimator is still going to be still going to yield me the same tau. And so what I'm going to use right here, e pi James Stein x. I'm just going to use this one. So I'm going to take a weighting of this. So same thing, all I did is I just shrunk everything towards 0, right there. And they entertain this in the paper. There's a big lofty discussion about the possibility of this being negative right here. And I'll come back around to that later. So, but in terms of an estimation technique, I never said anything about, you know, positive or negativeness, but obviously, if you're thinking about all of these as positive, and you knew that they were positive, this estimator could come back and it could give you something that's negative. I'll just remind you, this is theta hat I. I'll put the James Stein up here. So that's the estimator for I goes from 1 to p. Turns out this one still enjoys the same theoretical benefits of James Stein estimators. So let me go to my computer and I'm going to do a sim for you. I'll just remind you also, maybe just 1 second, Sierra. Let me say one more thing about this. What we're going to be looking at is we're going to be looking at the risk for all of this. So we need to examine risk. So that's how we decide if we're better. Remember, it's not just one data set that you're better on average across the data sets. That's what we're trying to do. So what we want to do is we want to look at this estimator right here. We're looking at the L2 loss function. That's why we use the Bayesian mean in the first place, so they presupposed L2 in all of this. So we're going to be looking at E pi, James Stein, that thing right here. Let me write it like this. We've got lots of names for the same thing. I'll call it theta hat I. That's my James Stein estimator. Minus theta I squared. What I'm doing is I'm integrating this thing over, oh, and I should put this in a norm space. Fx given all of my true thetas, 1 to p dx. So I'm going to be looking at this risk function. Remember that this risk function right here is p-dimensional. It's a little bit hard to view. So I need this thing right here for all my different i's. So I can't plot that for you. So I'm going to show you everything plotted in a normed version of all of this. Okay. What I want to say about this right here is this integration right here has this thing being plugged in here. I can't do it. I don't know how. I don't know how to integrate that. And it can be difficult to do. So in general, these calculations are hard to do. You can't even do the integral if I gave you the estimator. So what I can do is I can always do Monte Carlo. So I can estimate how good this thing is by sampling different data sets, looking at my norm, my squared error loss. So my MSE is what I'm plugging in right here. So this is just my MSE function. Mean squared error. Theta hat I minus theta I squared. And I'm just looking over the mean of these. So that's what's going up here. So I'm computing this thing right here, where this is a function of that data set. So I can always do Monte Carlo. Sample from this distribution, compute that. Do it again and again and again and average those numbers. And eventually, I'll close in on what this is. So some of our old tricks, Monte Carlo tricks. And that's what I'm going to do for you in my simulation. So let's just do that real quickly. Okay, Sierra. We're ready now. Okay. This code is up online for you, so you can look at this, you can play around with it. I have some parts commented out, so if you want to play this thing in different settings, you'll have to say what you're actually going to plot out. But what this does is it samples some data, and it samples some thetas. So what I'm going to do is I'm going to sample some thetas right here. So these are true thetas. all I'm doing is I'm uniformly grabbing thetas. So I have some uniform between 0 and 5. Those are my thetas. And I'm going to do this p times. Grab these things. So I have different thetas. And then I'm going to grab some different data points. So this is all just simulation stuff. So I'm going to grab my data point from my true theta. So I have true theta, and I add in a little bit of normal error. How much variance? Sigma squared, same as in the paper. And I'm going to compute my risk right away as we go. So I just have this rolling risk function. This is just computing the squared error norm on everything. So I started the risk at 0, I generate a data point, I compute the squared error difference right away for you. And then I just do this over and over again. I do this and I repeat it for the Monte Carlo number of samples so that I can compute this average on the risk function. So I normalize everything, and this is my Monte Carlo estimate of the risk. And I'm going to do that for different values of theta as well. I'll let you look through that. You don't need to change any of that stuff up there. So you can bend your mind over that code, but I'm just simulating a Monte Carlo thing. If you want to crank up the number of Monte Carlo samples and get more precision, you can do that. If you want to play around with the dimensionality of this problem, you can do that as well. My dimension is 10, so I can exacerbate this Stein result. It happens more and more as the dimensionality increases. And then I'm going to plot for you that risk. Here's what I'm going to do first. Is I'm going to do this for the MLE. So this is the MLE. X is the MLE that I'm plugging in right here. I probably should have said that. And that's what I'm comparing. So this is just for the MLE. Down below, I have this exactly set up exactly the same with different risk functions. So this is called the James-Stein positive parts method, where I just take positive James-Stein stuff. Nothing theoretical can be said really about that. People do it sometimes. And down below is the James-Stein risk. Let's just run this thing just for the MLE. So my code's all ready to go. And I'm going to do that for you. That's what I get right here. I'll show you a cleaner picture of this in just one moment. But for all these norm theta values, so my 10-dimensional theta value, I have plotted down here, and this is my risk function. And these are my Monte Carlo estimates of all that risk function. I've also drawn a straight line straight through this. Turns out I didn't need to do any of this. So this is the risk function for the MLE, just the xi's. And I actually know what the risk function is for using the xi's, or x bar. And so if I were using x bar, then my error is sigma squared over n. But since I'm just using the xi's themselves and I'm not averaging them all together, the p times, then my risk is sigma squared times p in this whole space. You can verify that to yourself, but the expected squared error loss when I'm plugging in the mean, or the mean from one value, is going to be a variance. And that's this. So that's actually the theoretical risk of the MLE. And this is my Monte Carlo estimate of it. And so you can go to my code, and you can crank up the number of Monte Carlo samples until this is as close as you want it to be to that line. So if I crank up n, the number of Monte Carlo samples, everything takes a little bit longer to run. But that gets closer to the theoretical truth. And I did that for you. If you look at the scale here, we got a lot closer to the line. This is 9.85. It used to be about 10.2 on the other side. So this is 10.05, and before it used to be about 10.2 or so. So everything got closer to the line. That's my Monte Carlo pair. So if I'm going to analyze this, which risk is lower, I better let you know that I'm not analyzing Monte Carlo pair. And so you have a little bit of control over that. I've already made all these plots for you. That code will help you make those plots. But I made these in advance. So I just have my little piece of code in there. So the thing I just showed you was this picture, and I've labeled it here. You can make your own. So this is Monte Carlo error, that's the truth. And I can bring down that error as low as I want if I crank up the Monte Carlo samples a lot. Now what I'm going to do is I'm going to draw for you the James Stein risk. It's this curve. And that's my MLE right here. So sigma squared times 10. In my example, I used sigma squared was equal to 1. P is 10, so the variance is 10 for the MLE. That's the same as the variance. And you can see how much Monte Carlo error I've got right there in this picture if you squint. You can see the little flutter in the James Stein thing. So in my code, what you'll do is you'll go down to just what's being plotted. Everything is being computed in the example. So if you want this to superimpose everything, uncomment the plotting function for the James Stein estimator. Everything else is coded upright. So you can imagine that this thing right here asymptotes down below. That's what we're actually seeing. And a better mathematician would prove that to you. And that's what people debated about for a long time. No way. So what we can see is the MLE right here is inadmissible to all of this. It turns out in this thing right here, this is never going to cross it. Turns out this one is minimax. Over here, the xi's is an estimator. And this one is going to asymptote into it, and its maximal risk is going to be the same as that one. So it turns out, for reasons beyond our theory in this class, this is also minimax. And I'll let a better mathematician tell you about that. What I can say about this estimator, because I shrunk all my estimates, and remember what this x-axis is, this is the norm on all of thetas. So it's just my squared error norm so I can order everything. But when my thetas are close to 0, I do really well. And remember how I constructed my prior. I picked my prior to center everything at 0. So I shrunk all of the estimates towards 0. And it turns out that when I'm estimating things around 0, I do well. Because I biased the problem there with my prior. This is not surprising. What is a little bit surprising is this never climbs above that. And so the paradoxical part is because all of these thetas are presumably unrelated. All of the xi's are unrelated because the thetas are unrelated to each other. I build in this controlling mechanism. I shrink everything towards mu. You're actually regularizing the error. Let's turn on the lights for a second. And I want to give you a caveat to all of this. Let's think about an actual example. Let's think about, I want to optimize something out there. I've got seemingly unrelated things. Let's imagine in all of this, these were really unrelated. They are not in my example, but let's imagine these were all IID things. So, healthcare system, whatever I'm trying to do there. Dow. the economy, whatever I'm trying to do there. Loss of life due to COVID, loss of life due to other things, unrelated, maybe totally different diseases, and all of that. If you want to be best on average across all of those things, you need to entangle all that seemingly unrelated information into your decision. And so a James Stein estimator can help you on the totality of your error. But on each one of them, it doesn't say that you're actually better. So let me think about a simpler example, maybe a little less contentious. Let's imagine I lived in some alternate universes, okay, so that these things really are different. Tea prices in universe 1, bowling ball prices in universe 2, hay prices in universe 3, and that's enough for my example, even though my James Stein estimator that we developed had to be 4 or greater. The general theory is 3 or more, so this will work with 3. You'd need to moment match or do something so that p minus 3 didn't appear. And it turns out in an empirical Bayes, you don't have to moment match. If we did maximum likelihood right there, that would also be an empirical Bayesian estimate, and we wouldn't have that hiccup. So you can do it in a number of different ways. But I've got these 3 different prices from these alternate universes, and their economies don't cross over each other. They have nothing to do with each other. What I'm saying with James Stein estimation is I'm going to try to estimate all 3 of those. I get to see a realization of those, or maybe multiple realizations, and I average. I look at the MLE. What it's saying is that to estimate bowling ball prices, I should look at the tea prices and the hay prices from these other universes that don't interact with each other, and I should use those in my estimation. And James Stein says that if I'm going to consider the error of all 3 of those things simultaneously, then it's best to combine. Here's the caveat. Sometimes I don't care about estimating everything else. I only estimate, maybe I'm only interested in bowling ball prices. I don't care, and I don't want to be scored for hay prices. Whatever estimates people are out there with hay prices or tea prices, I don't want that to be in the scoring when I consider how well I did with bowling ball prices. If that's true, then my best estimator, if I'm only going to score myself on bowling ball prices, it's the mean of bowling ball prices, or just one of those realizations. If I'm going to score myself on the whole network of prices, then I can do better by taking IID realizations and entangling them. And it gives us some error control and everything, and we see that in this risk function. So it depends on what you want to do. So one way you could misinterpret this is to say, hey, Scotland told me that if I just include all this other data into my estimates for things, I can estimate bowling ball prices better. You cannot do that. You can estimate the whole group of things better. Wikipedia has some nice conversations about it. They talk about cell networks, that it's important that your whole network is functioning, and that's what you're monitoring, not the individuals itself. And so my take-home point is that in a Bayesian analysis, you can do better on average if you steer the prior in a certain area. So if I say, I want to shrink everything towards 0, I'm going to do better when I estimate things towards 0. No surprise. And that makes my estimator admissible, and I might also get some other good properties. That could also hurt you. If I steer everything towards 0, while I can make this claim about some form of optimality, if the thetas weren't by 0 in the first place, then I'm going to be doing poorly all the time. And so I bias the problem to something that I don't want to solve. Proving minimaximality of things can be difficult in general. I like the Bayesian paradigm because it at least gives me an operating procedure. I come up with the posterior distribution, and depending on your utility functions, I'll pluck an estimator out of that. I know how to do that. On average, I'm great. I'm not necessarily shielding against the maximal risk out there, but I could if I want to flatten out that whole risk curve. And I can do that by turning the knobs in the prior. Again, in all of that, we're really just saying we're going to be better on average somewhere. Let's just steer where we're better on average or something like that. I want to be constantly good across the whole parameter space. There's prices to pay for that. And so I think in real statistical problems, there are certain thetas that we're more interested in estimating than others. And that will determine what optimality maybe means to you. So decision theory is hard. There are some operating principles. But again, the goal is to minimize risk, but you have to talk about what thetas you're minimizing for. So I have a few problems out to you on the midterm that walk you through this exercise. There's much more to discuss here. We're going to move on to hypothesis testing and get into this big debate. There's 2 papers online about p-values, and you've probably heard some people make some arguments about utilization of p-values, when to use them, when not to use them. So prime yourself with that conversation. Read over the empirical Bayes thing if you'd like, and bring your questions on Friday, because we can answer all of those. So that's it for now, you guys. Thanks so much.